students, good evening. Welcome to this video session. I remain Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall continue our discussion on gas laws, the laws of gases. And in this session, we shall discuss Dalton's Law of partial pressures. So you just log into my website, www.samdomforpeace.com, and under chemistry, you click on gas laws, and you will see the transcript of this video and also the solved examples on these gas laws. So we are going to explain the law and look at the formulas that we are going to use to solve questions concerning Dalton's law. Okay. Dalton's law of partial pressures, this is a law that is attributed to John Dalton. So what does this state? It states that when you have a closed container and you have a mixture of gases that do not react, mixture of unreactive gases. So it has to be a closed container, otherwise the gas will evaporate. And also it has to be a mixture of more than one gas, at least two gases that do not react. Okay, that is a mixture, so it's not a compound. So a mixture of gases that do not react. If you have this in a closed container, it states that the total pressure of the mixture of gases is equal to the sum of the pressures of the individual gases in the mixture. So total pressure of the entire mixture of gases in the container is equal to the sum of the individual pressures of the individual gases. Okay, so a gas molecule exerts a pressure, which is the gas pressure. So the total pressure exerted by the whole mixture of the gases is the sum of the pressures exerted by the individual gases. So let's say we have, a closed container. Let's say we have a closed container. It's closed. Okay. And you have let's say we have two gases. Okay, gas A and gas B. Okay. Let's say maybe gas A is, carbon 4 oxide, which is your carbon dioxide, and then your oxygen. Okay, so let's say you have these gases that do not react chemically. So normally they don't react chemically. So now we have let's say we have something like this. So these are gas molecules. Let's say this one is carbon 4 oxide. Is this gas molecule? And I'm going to use a yellow chalk. I'm going to use a yellow chalk and use another. Let me use triangle this time. Let's say we have this as oxygen. So let's say we have this as the oxygen gas, like this. Okay. So this is the oxygen gas here. So what Dalton's law is stating is that I'm gonna use this P underscore total as the total pressure exerted by carbon dioxide and oxygen. That's P total. Okay? And let me just call P of A as the pressure exerted by gas A, which is carbon dioxide. And then P subscript B is the pressure exerted by the oxygen gas. So you have it in a closed container. The gases do not react chemically together. Okay, at room temperature or at any temperature at all, okay, it does not react chemically together. It's saying that the total pressure, P total, exerted by the mixture of the gases is the sum of the pressures, partial pressures now. This is now partial pressures, which is the pressures of the individual gases. The sum of the partial pressures exerted by the individual gases in the mixture. Okay, so this is one formula. This is the main formula for Dalton's law. And it must not be only two gases. It could be just a mixture of gases, as many as possible. Now, I'm going to call this first formula, okay? Because in the questions that we are going to be using, I'm going to call this first formula. In the questions that we shall solve in this topic, we are going to use these formulas to solve it. Okay, so but I want you to understand the concept and how we derive these formulas. So that way, when you're looking at the way I solved it, if you go to the website and you look at the way I solved it, it will make meaning to you. Okay, and as usual, I explained it very well. But if you have any questions, feel free to ask. Okay. So this is our first formula. Now, if you collect a gas over water, sometimes when you're producing gases, or you collect gas over water. If you collect a gas over water, then it's likely that the gas is saturated with water vapor. So, and if it is saturated with water vapor, you will need to find the pressure of the dry gas. Okay, if it's saturated with water vapor, it's wet. Okay, it's a wet gas. So you will need to find the pressure of the dry gas. So if, say we have just gas, if a gas is collected over water, okay, it's likely saturated with water vapor. So the total pressure in this case will be the partial pressure of the dry gas plus the partial pressure of water vapor. And I am using water vapor here because I noticed that in my chemistry channel on YouTube, most of the subscribers there are Africans, not just Nigerians. So, and I am trying to help. I'm helping everybody, okay? But I'm paying like particular attention to Nigerians. You know, I taught chemistry here for 1 year, and since then I've not been teaching it full time. Okay, I've not been teaching it full time. So please, I know America here we have water vapor. The U is not there. Okay, but this is assuming it's Africans. We put U. Okay, we were colonized by Britain, and British they put U, vapor, P-O-V-A-P-O-U-R. Yeah. But hey, please, I'm doing it for everybody. It's just that I'm writing water vapor. So if you're American, just know that this is, I know you don't put U here. Okay. So, but don't stress out why I put U. It's Nigerian way. Okay. All right. So this is our second formula. Let's call this our second formula. So we take note of this. If we collect a gas over water, it is likely saturated. It is likely saturated with water vapor. So in that case, if you want to find the pressure of the dry gas, the pressure of the dry gas will now be the total pressure minus the total pressure of the gas, the mixture of the gas and the water vapor, minus the saturated vapor pressure. Okay, SVP. You know, Nigeria will say SVP, saturated vapor pressure of water. That is the pressure of the water vapor. You know, they will say SVP, saturated vapor pressure of water at that particular temperature. Okay, so that's the second formula. Now, I would like you to pay attention. Let us find the third formula. So, from the ideal gas equation, okay, from the ideal gas equation, because some questions would might not be straightforward for you to use this first or second formula. You know, they twist questions. So, and Americans should pay attention this way. Everybody pay attention anyway. But some questions like Americans ask would not be straightforward because they want you to do extra work to, you know, there's a third formula we need, and I want to explain it. From the ideal gas equation, we have that PV is equal to N RT, N times R times T. And this is the ideal gas equation. Your R is the molar gas constant, of course. That's the molar gas constant. And it has several values. It is normally given, but whatever value, you know, in the in AP chemistry, they give you several values of the molar gas constant. You need to be careful which value to use. Okay, you have to be consistent. You have to make sure that the value of the molar gas constant you use, that the unit of that molar gas constant that you're using should be consistent, corresponding units with the units of the other variables here. Okay, so they will give you the molar gas constant, and you know, and you make sure that the units are consistent with the other variables. So this is a constant. Okay. Now, This is a closed container. Because you have this as a closed container, the volume of gas A is equal to the volume of gas B, which is the volume of the container. Okay? This is the volume, like if you take only gas A, which is carbon dioxide, okay, if you just take it out in this vessel, okay, see what I'm saying here? If you take this, if you have only carbon dioxide, and then you have only oxygen, so let's say you have only oxygen, the volume occupied, and I know this looks bigger, but let's say it's just the same container. Okay, let's say it's the same container. The volume occupied, like a gas fills up the entire volume. Okay, if you get, like 20 cm³ of oxygen and you put it in a container that has about 40 cm³, the gas will occupy the whole volume. Okay, a gas molecule occupies the entire volume of the container. So if you have this, it's the same thing. It's the same thing. I know that you will say, some people might say, oh, Mr. C, that the container, that this one is bigger. Just assume it's equal. Assume it's the same container. Okay, the gas molecule will occupy the entire volume. So in that case, the volume of the carbon dioxide will be equal to the volume of the oxygen, which is the volume of the container, to fill up the entire container. Okay? So the V is constant in this case. Also, the temperature. The temperature of the carbon dioxide will be the same temperature of the oxygen, which is the temperature of the container. Now, the only thing that varies now is the pressure. Okay, the partial pressure of carbon dioxide might be different from the partial pressure of oxygen. Okay, likely to be different because it's going to be different anyway because of their what? Because of their number of moles, which is indirectly because of their molar masses. This has a molar mass of 44 grams, 32 plus 12, 44. And this has a molar mass of 32 grams. So it's different molar masses. Okay. So the P of the partial pressure will be different and the number of moles will be different. Okay. So because sometimes you are given only number of moles and or the reacting masses. Okay, they expect you to know the molar mass anyway. They give you the reacting masses and they want you to find the partial pressure. And then you might say, hey, how do I find it? It's not in the first formula, it's not in the second formula. So let's see how you can find that. Okay? Sometimes some questions will just give you the reacting masses. Okay. Alright, so the only thing that differs is the pressure and the pressure and the number of moles of each gas molecule. So what we are going to do now is, I'm going to erase this. So we now have from here, okay, we know that for gas A, which is the CO2, we know that P of A times V of A is equal to N of A times R, which is a constant, times T of A. Okay? But V of A is the V, T of A is T. So this is P of A times V is N of A, N subscript A, that is the number of moles of gas A, okay, times R times T. So we now have that P of A over N of A is equal to RT over V. Okay? That is all we have for gas A. RT over V is equal to P of A, the pressure of gas A, which is the partial pressure, of course, by gas A, the ratio of the partial pressure of A to the number of moles of gas A. Okay, the ratio of the partial pressure exerted by carbon dioxide to the number of moles exerted by carbon dioxide. Similarly, for gas B, which is your oxygen, we now have that the ratio of the partial pressure exerted by oxygen to the number of moles exerted by oxygen will give us RT over V. Okay, similarly, this gives us this. Right? RT over V. Okay, we are coming to somewhere, okay? Now, we are now going to look at the total pressure now. The total pressure, if we consider gases A and B, okay, which is your carbon dioxide and oxygen. We now have that PV is equal to nRT, that is the ideal gas equation. And of course our P total is the PA, partial pressure of the carbon dioxide plus partial pressure of the oxygen gas. Also the total of the number of moles is the number of moles of carbon dioxide and the number of moles of oxygen. That is the total number of moles. Okay. So we now have that this implies that the total pressure is equal to the number of moles total times R. Okay, this times V. Okay, the total pressure times the volume. Okay, the volume of the container, volume occupied by both gases, which is the same as the volume of the container, is equal to the total number of moles times the molar gas constant times the temperature. Right? So we now have that RT over V, the ratio of the total pressure to the total number of moles is equal to RT over V, just like we have here. Right? Okay, so now we now finish up what we are trying to do. We now finish it up. So we now have that from gas A, going back to gas A, the ratio of the partial pressure exerted by the gas A, which is the carbon dioxide, to the number of moles of the gas A is equal to RT over V. Okay, now, so this RT over V is the same thing as the total pressure over the total number of moles. So this is something as the total pressure over total number of moles. Okay? But RT over V is the total pressure over the total number of moles. So this means that the partial pressure of gas A is the number of moles of gas A times the total pressure over the total number of moles. And this now implies that gas A, the partial pressure exerted by gas A is equal to the mole ratio, okay, times the total pressure. So this is your third formula. This is your third formula. So as you can see here, the partial pressure of the gas, another way to calculate it is the mole ratio of the gas to the total number of moles times the total pressure. Yeah. Because sometimes what they do is sometimes they give you the reacting masses. I mean, they give you the mass in grams. I know they don't react, but they give you the mass in grams. Of course, you know that the number of moles is the reacting mass over the molar mass. So sometimes they give you the mass in grams of the gases, and they give you the at the relative atomic masses of each atom. Okay, they give you the relative atomic masses of each atom. C is 12, O is 16, and of course they will not want you to give you the molar mass because they expect you to find the molar mass. Okay, and then when you find the molar mass, you now find the number of moles by using this, and then you can get the partial pressure of the gas. Okay, so I hope it makes sense. Okay, I hope it makes sense. And similarly, we also have that the partial pressure of gas B is the mole ratio of gas B. The mole ratio I'm talking about is the ratio of the number of moles of gas B to the total number of moles, then times the total pressure. Okay? Alright, we shall stop here for tonight. Continue with me. We are going to solve more problems on gas laws, and then we start solving problems on stoichiometry. Stoichiometry should not be difficult at all. Honestly, you should not find it difficult at all. Okay, so just keep checking on. Hopefully, by the grace of God, when I have time, I will keep on uploading more resources. Okay, so keep checking on. This site mainly will contain chemistry, so you can look at those. All right, if you have any questions, please feel free to ask me. Okay, thank you so much for listening, and you have a good night.